Good afternoon. My name is Bob D. Hilster, and I am presenting a paper at the CNPS 2019
Closer, please.
conference. And
Closer,
the paper...
Closer, please. I did not see. Go closer. There you go. Thank you. Sorry.
The mic is now closer.
Thank you.
The paper is on the particle model, which attempts to explain how parallel resistors work. In general, the agenda will be oh, you got my old slide. I deleted the wrong one. I will, but not first. The TPM Circuit will come, but not first. I'll do the standard explanation, the particle model explanation, and then a possible experiment. This is a circuit that I am using. It's similar to one I used in the previous paper, 9 volts with a 4K, 2K, but the 2K is made out of a 3K and a 6K resistor in parallel, and then a 3K giving you a total of 9K ohms, powered by a 9 volt battery, giving 1 milliamp of current flowing out of the positive end of the battery and around, and that's a current model. Okay, there is a standard equation for parallel resistors. I could have shown you how to derive it, but it's simple. The total resistance of a parallel resistor is the product of the two resistors divided by the sum. In this case, it's 3K times 16K is 18K over 9K, making a 2K net total resistance. And it works. But the standard model has no physical explanation for how it works. They have an equation to explain how to know what the value is, but that's not explaining how it works. Okay, I want to point out initially that the R1 and R2 current has to split. And if the net value of the two resistors is 2K, then the voltage around them will be 2 volts. So each resistor has 2 volts around it. And so you take the 3K resistor, divide 3K into 2 volts, you'll get 2/3 of a milliamp of current into the 3K, and you get 1/3 of a milliamp into the 6K. This circuit will always have these values, every time. These values are deterministic. It repeats over and over and over. It's not like it's some coincidence, like tomorrow morning it'll be different. It'll be the same. Okay, now in the particle model, I have one of the assumptions is that there's a G2 gravitational field and a G1 gravitational field around all objects, G1 and G2. G1 gravity pushes the circuit towards the center of the earth, and thankfully my circuit stayed on the table. G1 gravity is pushing it down. G2 gravity causes particles or electrons to change direction or change speed, or both, depending on the net force of the G2 gravity around the resistors and then around the particle itself. G2 gravity, I've said this in other conferences, that G2 gravity is the nuclear binding force, the atomic binding force, and the molecular binding force. It's holding them at the G1 level. We have something holding the Earth together, and something holding our solar system together. We have something holding the whole galaxy together like a big molecule. G2 does the same thing at one level down. Okay, so this is the particle model circuit. Instead of electrons coming around here, normally you'd worry about the split of the current right here at this connection. But in the particle model, we're following electrons or G1 particles flowing in this direction and around. So what we're concerned about here is the split of the current at that point. So And the G2 particles, these are, the blue lines are the G2 particles surrounding it. Not in any particular order here, just to show it's surrounding it. And they are moving very fast, as I pointed offline. Or my opinion is they come from subatomic atoms. They're subatomic orbitals moving very fast at a very high speed. If you're going to bend light, you can't be moving at speed c. A particle moving at speed c will not push. It'll meet up with, it'll touch, it'll go along with, but it couldn't bend it, slow it down, or speed it up. Has to be moving very fast. Okay, so finding the right path. How do the G1 particles know which way to go? They don't. The physical connection might split them 50-50. G1's coming in here, my 50 may go this, 50% this way, 50% that way, just because of the physical opening, or 60-40 or whatever. It might be 50-50, but that isn't going to get a 2/3, 1/3 split. So I'm suggesting that the G2 gravity is the one that helps us do that. Now this was my first try, and I was wrong on my other presentation about the small resistor. Well, this turns out to be wrong also. The 6K is the larger resistance, so my initial thought would it have twice the loss. So here I've redone the G2 particles coming here through the 6K, have a big loss, leaving fewer particles here, the same number here as all of these on the outside are the same, giving a strong force this way, a small loss this way that leaves a lot of particles here, hence a smaller net force this way. So this model, if this statement is true, I get the split in the right percentage, but I get them going the wrong direction. It's the wrong split. So I had to go look at the resistor itself and stumbled onto this website and this equation. Now, actually, I learned this equation. I remember this equation from college, but since I never designed resistors, I had no reason to use it, and I had actually forgotten about it, but sure enough, I said, oh yeah, that one. In simple words, the resistance R of some material increases as its length increases. The length goes up, resistance goes up. So longer wires offer more resistance. And it increases as the area decreases. So the area goes down, the resistance goes up. And the thinner wires offer more resistance. The resistance is also related to the type of material from which a resistor is made. And that's indicated in the equation by the symbol rho, which is called the resistivity and defined in units of ohms meters. Now, this is just another empirical equation amongst all of many, many, many empirical equations. I forget who did this, but he went through a lot of resistor material, made them longer, made them shorter, make them wider, make them narrower, plotted them on a curve, found the curve was a straight line for a given material, develops the equation. It's an empirical equation, but it helps explain, in this case, what might be going on. So it's the physical size of the 3K and 6K resistors that I started looking at, the length and the area. I made these two resistors the same length, and I made this area twice the area of the 3K, twice the area of the 6K. And so in terms of resistance, I'm assuming I got two carbon comp resistors of the same length, but the 3K has twice the volume of the 6K. There is more room for the G1 to pass through this than there is room for it to pass through there. It's going to interact, it's going to have a higher interaction because of the value of the resistance, and this has a lower interaction because of the value of the resistance. But the physical side is exactly the opposite. The 3K is twice the volume of this. G2 mass is my term for, we have G1 mass, which is equivalent to the kilogram standard. G2 mass is the mass of the object that the G2 particle interacts with. What I found over time is that most of the time, the primary element is the G1 particle. I'm sure the nucleus is into it and whatever else, but I generally use that as my initial way to evaluate. So the 3K has twice as many G1s as the 6K, and I claim it has twice the mass. The G2s, well, 3K has twice as many G1s as the 6K. The loss of the G2s passing through the 3K will be twice the loss through the 6K. I'll get more loss through the 3K, less through the 6K. And so now I redid that same figure. I'm going to get more loss this way, so now I have fewer G1s here and a stronger force that way, and I have, although there's some loss through here, not as many, so there's a weaker force this way, and the split will be 2/3 of the ones coming in. 2/3 will go that way, 1/3 will go that way, and it's all controlled already at the connection point where it has to be. If it doesn't happen there, I have no other place. So something might happen up here with these forces. Could happen, something could happen up there. Frankly, I tried this over and over, and I didn't get very far with it. I tried this first, and then I went down here and got better results. Okay, now that previous figure was without any G1s flowing. I was only considering the G1s in the resistors themselves. But as soon as the G1s start flowing, these forces are there, they're ready. With one G1 going this way, you get two going that way. One this way, two. And it's statistical in nature. Any one time, it might be a little off. Maybe more or less, but on the average, it's going to be split. Okay, now I'm already on to the experiment. I'm going to do an experiment with parallel resistors and see if I can prove that this idea is valid. The overlapping G2 force fields are strong when the resistors are right next to each other. They are weaker as the resistors are separated. And I expect that they'll be reduced by 1/r², much like Coulomb's law. Step 1, set the two resistors 1/2 centimeter apart. Measure the length of time for the two resistors to reach 2 volts, because I'm only looking at those two, how long that's taking. Step 2, pull the second resistor. I don't have the picture there. Yeah, okay, set it 1 centimeter apart and then 2 centimeters apart, again measuring the length of time. We're going to measure time. And this is the layout. Here they're 1/2 centimeter apart. Then you take this one, you move it here, it's 1 centimeter apart, then you move it there, it's 2 centimeters apart. It's not, I didn't measure this out, I eyeballed it maybe. But I'm going to do those 3 measurements, 3 times. Let's take step 1 at 1/2 centimeter. I'm going to have the 9-volt resistor, 4K, 3K and 6K in parallel, then a 3K. Let it stabilize and measure, hit it with a pulse, a repeating pulse, and measure the rise time. Rise time is from 0 or 10% to 90% is standard way of measuring the rise time. After I've done step 2 and 3 for the same circuit, I will end up with 3 curves. And what I'm expecting to get is that the time from the second curve to the third curve will be 4 times the time between the first and the second curve. That's if it's being controlled by a field that's reducing by r². That's just a prediction. It's a doable experiment with a 6.5 digit voltmeter with automatic recording on a scope. digital storage scope. These experiments are quite easy to do. Okay, in summary, the electrical model, the standard model, cannot explain parallel resistors. The particle model has at least a possible answer. Just like my previous talk, I can't say this is the answer. All I can say is this is a possible answer, and there's a way to test it. Each resistor has its own G2 gravity field that overlaps the other resistors. At the same time, these two gravity fields overlap the connection point, and they provide proper force to guide the G1s through and thus provide the current needed through each resistor. Okay, as far as a summary of the experiment, the G2 force that overlaps, I think I'm repeating myself here, the force is weaker as you go further apart. However, it takes the whole circuit some time to get it the right number flowing in the first place. You saw in the previous spreadsheet, it takes some cycles to go, okay? Well, it's going to take maybe longer to accommodate these fields. I don't know exactly. If the parallel resistors take a longer period of time, it will delay the whole circuit, but the delay is what we're after in the first place. So I still think it's going to work, and if I have to, I can make the separations larger. Okay. A couple of years back, when I first talked about the particle model and G1 streams of light and so on, I was talking about how the G1s came out of a negative side of the battery, went through the circuit, into the antenna, and out as streams of FM signals. I'm not going to talk about that this time. What I am going to say is I got G1 particles coming out of the negative side, and it's got this whole connection point to deal with. How do the electrons know where to go? And you know they get to the right place at every time. It's deterministic. I'm not going to explain that. To me, it's mind-boggling to think that there's a G2 field all around this circuit and they're all overlapping and guiding the G1s. It's mind-boggling. Thank you. That's my presentation. Any questions?
Yes. Have you tried applying the particle model to other electrical components like the inductor?
I haven't. This is my first try doing any circuit experiments. I've done all three that I've planned. I've done two. First one I reported on in the other paper. Second one failed. I didn't get like 10% correlation. But I didn't have as good an instruments. I did manual recording. I had a battery that was drifting. I got to get a solid supply. I got to get automatic recording and a 7.5 digit meter. I'm going to repeat it. This experiment I just talked to you about, I haven't done. I'm sticking my neck out there. I'm saying that this is possible, and I haven't even done it. Okay? It could fail. But it would be interesting to do more. But I'm pretty sure that in an electrical sense, you'd have to really get into the inductor. Just do an inductor. And it has a back EMF. You know, how do you explain that back EMF in an inductor? How do you explain why the current is slower and the voltage is faster in an inductor? And then you got to play that all with the particle model and give an explanation. I got some work to do to answer your question.
Bob, in reply to Mrs. Question, my reaction is, good for you for giving it a try. Pure and simply that. If it doesn't work, it doesn't work. If it does, you may have a breakthrough of sorts on your hands. Thank you.
Thank you.
This is for either you or both you and Dave. Earlier you mentioned in your particle model, you've got your G1s, et cetera, going at the speed of light, correct?
Generally, yeah.
And,
They can be going incidentally faster or slower.
oh, so you don't use C as a limiting speed?
There is no upper limit even to
Okay.
the G1 particle. And I'll tell you why. That G2 force, for example, in a magnet, got a strong G2 force on either end of the magnet.
Closer mic, please, I can't hear you.
It's got a strong force at either end of the magnet, which means that it's pushing it, gravitationally pushing it. It's moving at speed c, it's going to push it faster until it gets to the middle, it's going to slow down. And then the other side, the force is going to slow it down, such that it would probably enter at c and leave at c. But it has a high speed, it's like a perihelion point of the Earth. And as it goes around and it's further away, it slows down and it goes slower. Out here it's like aphelion. And then it comes around and it speeds up. So it incrementally speeds up and slows down, and it does the same thing through a resistor. Speeds up a little bit, slows down.
To what extent then is your resistor model with the G particles analogous to like just water flow going through smaller and wider pipes where it's, it speeds up to get, because you got to get the same amount of water in and out at the same end, so it seems to have an analogy with that.
Yeah, you could have a pipe that wasn't linear, a pipe that went this way and this way.
Yeah.
And you'd have a speed up and slow down effect.
One, you had on mute.
I'm not going to.
That's all right, now.
That's it. Now that the mic works, any other questions?
I think one of the other things is that's extremely interesting is that the particle model is showing us, giving us a way to try to start to identify what's really physically happening in circuits. And what we're finding out, what my dad was finding out, is that it's predicting things that are different. And the only way you can see this is to get these ridiculously sensitive voltmeters. One of the things is when he was measuring the circuit, you could watch the battery draining. I mean, you put a battery on a circuit, it's not going to stay there forever. So you have to imagine that no one is doing this. No one's putting these things together.
In fact,
No one's going to rent a machine that's 6 digits and do this. Now you have to go to another one with one more level. Now you have to see, I think it's quite fascinating to me, because one of the things I said to my dad in the early part of our model was, I can't wait till you start applying this to the physical world of circuits. Because just like everything else in physics, you get the empirical equations, we use it all the time, its importance, but when you put resistors together and you have your equations come out with whole integer numbers, and that's really not what's happening, and you have a model that can at least predict it, right or wrong, that to me is what models are supposed to be doing. And I think these are the kinds of opportunities we have to actually say, okay, if we do have a model, can it predict something different, and what will come out of it. But when he's talking about, I'm going to try to perhaps get us to get a university professor who's not in physics to perhaps allow us to use some of the equipment and say, look, we're just doing experiments with components. We don't need to tell him about the model. We've got these predictions, where'd you get that? And then you go from there. But I think it's really quite amazing to do that. And I just want to say that it is quite commendable.
I knew after doing some that the battery was drifting. So when I connected the battery, I measured it at first, did the 3 voltages, came back, measured it again, did the average. But that's part of my problem with the data. It's still not the best it could be. But I averaged it, it's the only thing I could think of doing.
Any other questions? No? Okay. Thank you.